All right. So what I'm going to do is record like this short little video for you. Let me know if you have any questions, but these are super easy. My idea is to kind of talk about these four questions and just kind of like what you should expect to see in the lab and why you should expect to see it. I'll also send you a few other really good resources that I use in my own classroom. And you can let me know if you have any questions. But basically what we're looking at are position versus time graphs, right? And like any other graphs, these tell us about the relationship between two variables, right? So on I'll kind of have a bunch of graphs here. So this is our position graph. Ignore my cat in the background. Okay. So there's my position, there's my time. So basically, what we're going to do, we'll kind of look at these four scenarios. There you go. Shh. Sorry, my cat is going crazy. Um, we'll look at these four scenarios and we'll just kind of talk about what we should expect to see. So this first scenario says this is an object at rest. So in a position versus time graph, it tells us what position, just like its name says, it tells us where we're going to be in a certain amount of time. And before we jump into that, this is all in service of understanding velocity, right? So velocity we usually as like distance or displacement over time. And we're used to seeing velocity as like, um, miles per hour. So if you go 50, if you're moving at 20 miles per hour, okay, in 1 hour, that's 1 hour, you travel 20 miles, right? In 2 hours, you travel 40 miles, right? So in this case, we're used to seeing our velocity kind of shown to us like that. But in class, you're probably going to use meters per second. So we'll put meters here and then seconds here. Okay. So um, all we're doing is what I want you to picture is kind of like a clock that ticks every second. So let's delete this. So we'll have labels down here. We'll say this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, six, seven. 1, 2, 3, 4, 5, 6, 7. This should kind of get us enough of what we need to do. Um, so uh, our first thing here says an object at rest. So if I have like a thing and it's on a table and I get my clock out and I want to see where this thing is every second. So let's even like more simple than a table. Let's just like look at the ground here. Let's call this point 0. This is our position of 0. And we have a box sitting on the ground here. And if I get a stopwatch out and I track what happens at every second, well, what happens at this first second? Well, has it moved at all this first second? No, so its position is still at 0. Okay, if I let another second pass, 1/1000. If it's not moving, it's still in the same place, right? So I see another one. So if it's not moving again, every second that passes, I should see it stay in the same place. And if I connect all those dots, right? If I connect all those dots, I just get a flat line. So for an object at rest, this should be a flat line on our position versus time graph, right? Now, if I wanted to also turn this into a velocity versus time graph, let me just like copy and paste this just for it'll make sense in a second here. Okay. My cats are going crazy. I'm sorry if you heard that. Okay. Let me copy that so we can just use it. So, right, so if it's at rest, it should be a flat line, right? This is a flat line if the object is 0. But if I started the object, let's say I started the object over here instead at a position of like, let's call this a position of 5 meters, right? This is 5 meters, this is 0 meters. Okay. If this is 5 meters, then it's going to stay at 5 meters the whole time. And I'm just going to see like another flat line, right? So, sorry, I'm trying to change the color. Okay, right? So this is if it's at like 5 meters, and this is if it's at 0 meters. Depending on where you are, that tells you where your line is going to be. But every second that passes, that thing stays at the same position, right? So if I were to, the other thing that I'm probably going to expect them to maybe ask you, well, maybe. I don't know. It'll depend. I won't include it for right now because it might just like provide extra confusion. So one more time, I'll throw that red line on there. For an object staying still, we're going to see a flat position versus time graph. So next, this was. Let me go take care of my cats here. Hold on, they're going crazy. Okay. All right. Oh, mango. Okay. All right. Okay. So again, this was for scenario one, where an object's at rest, our position stays in the same place over time. Okay, pretty straightforward. It'll be, I think, even easier when we look at something that's moving. So if we look at something that's moving, let's talk about this for situation two. So I'll scroll down here. Hold on. Okay, let's look at situation two here. So this is now an object that's moving, right? Okay, so now let's picture the same object. It's hanging out on a table, but now it's moving. Okay. And let's say it moves 1 centimeter or 1 meter every second. So we'll call this spot 0 meters. We'll say this is 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. Okay. So if this is moving, let's say the object is moving at 1 meter per second. This is our velocity. Okay. Now, if the object's moving at 1 meter per second, I'm going to think about my stopwatch. So at 1 second, our object's right there. Or sorry, at 0 seconds, our object's at zero. So let's make a point for that, right? Zero, at a time of 0 seconds, our position is zero, right? Then let's see, okay, if it moves 1 meter per second, let's check our stopwatch, right? And when our stopwatch is at, let me turn this into like an actual box here. Okay, so sorry, let's use an actual. I'll like make an actual square. Okay, so when our thing is now at when 1 second has passed, our box is now at 1 meter. Okay, right? So looks like that. When another second has passed, our box is at 2 meters, right? And it's like I'm pretend kind of you have a stopwatch here, right? And you're checking where it is every second that passes. Okay, now our box is here, right? And every second that passes, I go 1 more meter. So I should have a graph that looks something like this, right? Now, I looked ahead and I looked at the questions that are on the next page, and this is the big thing. One of these questions is what's special about the velocity, or what's special about the slope of this graph? Well, here we said our velocity was 1 meter per second, right? It go every second that passes, it goes 1 meter. Well, here's what I want you to find. What's the slope of this line? Okay, the slope of this line is the change in y over the change in x, right? Delta y over delta x. Well, what's our change in y? Our change in y is our distance. So if I pick any 2 points on this line, let's say I picked these 2 points. It doesn't matter, right? I could pick any 2 points on this line. If I pick these 2 points, let's go 0, 0, and 5, 5, I can calculate the slope. And I know how to do that. That's just like rise over run, right? So we rose. How much did we go up by? Well, we went up by 5 meters, and we went over by 5 seconds, right? We went over by 5 seconds. So we went up 5 meters and over 5 seconds. So we'll kind of, yeah, how about this? Hold on. Okay. We went up 5 meters over 5 seconds. So our slope of this line is 1 meter per second. 5 meters in 5 seconds, that's 1. So our slope of this graph, this is situation 2, okay. Our slope of the position line is always our velocity, right? Our slope of the position graph is always our velocity, okay? So what if an object was going faster? What if we went 2 meters per second instead? All right, well, let's see what would happen, okay? If we went 2 meters per second, if we're going at 2 meters per second, okay, let's think about what our object is doing, okay? If we're going 2 meters per second, this is 0, 1, 2, 3, 4, 5 meters, right? These are all in meters, okay, right? These are all in meters. If we're going 2 meters per second, let's track it. So at a time of 0, or at a time of, let me make a box here. At a time of 0 seconds, okay, at a time of 0 seconds, we're at 0 meters. Okay, that makes sense. I'm moving 2 meters per second, right? So let's do that point. And then V is 2 meters per second. Okay, so boom. So let's grab this, and when 1 second passes, we move. We're going to go here and check that out. So now after 1 second has passed, we have another point, and now our point's here. And after another second passes, we're at 4 meters. And then da 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 da. Now, there we go. So I'll write a couple important points in gold here, right? So our important point was here is the slope of position graph is equal to the velocity, right? And down here, when we saw a steeper slope, means the object moves fast, and then the opposite, right? Shallow slope equals object moves slow. Okay, cool. So that's your first scenario that you're going to see in the lab. Your second scenario you're going to see in the lab as well. Your third scenario you're going to see in the lab is an object moving in the negative direction with a constant speed. So now, instead of moving from left to right, we're going to move from right to left, which is what we call the negative direction. Okay, so let's put this here. Okay, we'll use another position graph. And this time, well, let's start at 5 meters, right? Let's go 0, 1, 2, 3, 4. And now our box is going to start over here, right? Okay, so when we're at 0 seconds, think about your stopwatch. Let's let our stopwatch run for 0 seconds. When we're at 0 seconds, I now have, when we're at 0 seconds, I'm at 5 meters. Okay, and let's make our velocity -1 meter per second. So now we're moving right to left. Okay, so let's let 1 second pass. Well, after 1 second passes, after 1 second passes, we're going to be at 4 meters, right? So we're going to go out to 1 second. We're going to go up to 4. and plot a point there. After another second passes, we're going to be at 3 meters. Or sorry, 2 meters. No. After another second passes, we're going to be at 3 meters, right? Because another second passed, we went back, boom, boom, until we get to 0, right? And if we put a line in there, okay, and we calculate its slope, ready? If we calculate that guy's slope, our slope is the change in y over the change in x, right? So how much did we rise by? Well, we rose by -5. That was our rise. -5 is meters, is how much our y changed. And our x changed by 5 seconds. Okay, so our velocity is -1 meter per second, right? Again, the slope of this line is your velocity. So this is kind of our other big idea here. This is our other big idea. We'll put it in gold, that a negative slope equals right to left, and positive slope equals left to right, right? So these slopes up here were all positive. This is our first negative slope, and we know that because it's now moving, it's moving backwards now, right? It's moving right to left instead of left to right. Boom. So those are our big ideas, okay? Now our fourth, that was your third scenario, right? Let me make these black here just so it kind of blends in here. That was your second scenario, your third scenario, right? And then an object that's accelerating. Now this one's a little tricky. So acceleration means that our velocity constantly changes. Or no, sorry, this was your third scenario, not that. Okay. Now our velocity, so our acceleration means that our velocity is constantly changing. And you and I can work together on this on Tuesday because this is a little bit trickier, but not really. Oh, oh boy. Okay, let's try and take this graph. Okay, copy. Okay, and oh boy. Oh boy. Sorry. It's being weird. Okay. So I'm just gonna redo this. How about this? Try one more thing here. Let's duplicate. There we go. How about that? Oh, perfect. Okay. So now for acceleration, it's going to be a little bit different. Acceleration means that our velocity is constantly changing. Okay. So our velocity never stays the same, which means our slope also never stays the same. All right. Ignore these little green dots. Okay. Can we get rid of them? There we go. Good. Okay. So now we're accelerating means we constantly change our velocity. So instead of moving at a constant velocity, we're moving at an ever changing velocity. So let's look at our number line. We'll call it 0, 1, 2, 3, 4, 5, 6, 7, and I'm going to go all the way up to 8 for this one. So now, let's say that the position, this is a square. So when an object accelerates, this is a little tougher, and we'll talk about this together. But When I have my box here at 0 seconds, think about our stopwatch. Let's track him every second. So at 0 seconds, he hasn't moved at all, right? This is 0, 0 down there. Then when 1 second passes, he moves 1 meter. Okay, we've seen that before. That's nothing crazy. All right, but then when 2 seconds pass, what if he moves 4 meters? Okay. And then if 2 seconds pass, he moves 4 meters. So I'll go out 2 and over 4 on my graph. And then when 3 seconds pass, he's moving at 9 meters. So the big idea here is that this line is curvy. Okay. Right? So now this is an acceleration. So this kind of brings us to the third big point here is what happens when an object accelerates. So a straight line is the constant velocity. And a curvy line means that our velocity is constantly changing, means a changing velocity. And acceleration. Because if we think about this as like slope, if we think about it rise over run, okay, rise over run, right? That's our first one, okay. But then our rise over run between these 2 points is different. And then our rise over run between these 2 points is different. So our slope always changes, which is what makes this acceleration. Okay, so hopefully that helps. Again, I'm gonna kind of be busy this weekend, uh, but yeah, I think we hit all 4 of these. And again, steeper slope means that we go faster, less slope means we go slower. And the big idea here is if you can find the slope of this line, you can find the velocity because the velocity is always going to be the slope. I think maybe real quick, let's talk about, I think if you want to describe the analysis, right? So I'll kind of just like mark this up here, and I'll send you this as well. Our analysis, right? This is just kind of, you're going to describe the slope of this. This is the velocity, is the slope. What kind of motion is occurring when the slope is 0? Well, you know, if the slope is 0, are we moving? No. That means we're still. We're standing still. What kind of motion is occurring when the slope is constant? That means we have a constant, meaning not changing and not changing velocity. Right? We'll color code this here. Right? That means we're staying still. That means we have a constant velocity. What does it mean when the uh, what does it mean when the slope of this graph is changing? Okay, that means we have acceleration. Okay. And then what type of motion is occurring if the slope of the velocity versus time graph is 0? This is a little bit new. I'm going to send you a video that talks about this in a little bit more depth. But the velocity graph would be, this means that we're have a constant velocity. This means that we have a constant velocity. And the reason for that is because our velocity is not changing. So the slope, if we made a velocity graph, maybe we'll jump back and do that really quick. But if we made a velocity graph, the slope wouldn't change. And then this would mean, then this last guy would mean that we have acceleration. I'm going to send you a video that talks more about this, but this means acceleration. Yeah. Okay, so for example, let's look at a quick let's look at a quick example of like how to make a velocity versus time graph, and then we'll call it good. So let's see, down over here. Okay, let's make us a velocity graph of this guy. So I'm just going to copy this whole thing, and let's turn it into a velocity graph. So this graph told us how position changed over time. Now we're going to make a graph that tells us what velocity does over time. So if this is my ready, if this was my position graph, okay, I need to, it's being so sketchy, I'm sorry. Ay, ay, ay. Oh boy. Okay, let's do that. Come on. Okay, there we go, right? So this is my position graph. Let's turn this into a velocity graph. It's pretty straightforward. So I want you to ask yourself, did my velocity ever change or was it always 2? Right? Let's find rise over run. My rise is always 2, and my run is always 1. This is 2, and it's always 1. Right? So my velocity of this graph is equal to 2 meters per second, right? Which means I travel 2 meters every 1 second. So my velocity graph could just look like this, right? Velocity, right? My velocity graph, so I'm traveling for 4 seconds. So 1 second, and this is time. 1, 2, 3, 4 seconds. And yes. And how fast was I going? Well, this is 1 meter per second. This is in meters per second, right? And time is in seconds, right? Okay. 1, 2, 3, 4, 5, whatever. My velocity, okay, what was my velocity for this first chunk? Well, my velocity was 2 meters per second. All right, what's my velocity for this second chunk? Well, it's still 2 meters per second. My slope didn't change, right? So it's still 2 meters per second. Oh, that's not a point. 2 meters per second. What's my velocity during this third? Oh gosh, come on. During this third chunk. Okay, again, it's still 2 meters per second. So we know that this line is flat. So this is what my velocity versus time graph looks like. This is my velocity versus time graph, right? It's going 2 meters per second this whole time. And then for my acceleration, when I had acceleration, my velocity graph is going to be constantly increasing. It goes up by the same amount each time. So my velocity graph for this guy, and we'll talk about more about this later. It's kind of tough to talk about digitally, but I'll send you some resources. My velocity graph here, if this is now velocity, and this is time, I'm going to have a graph that looks something like this. So this is 1 meter per second, 2 meters per second, 3 meters per second, 4 meters per second, 5 meters per second, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So this graph is going to look something like this, because this rise over run was 1. This rise over run was 2, because we rose to 4 and we went over to 2. So that's 2. This rise over run up here is going to be 9 over 3, because we rose to 9 and we went over to 3. So that graph is going to look like this. So we should see something that accelerates like this. So this means if this slope is non-zero, if the slope of this velocity versus time graph is non-zero, that means acceleration, but we just talked about that. So I think that's a pretty good kind of look at this. Again, it's probably going to be tough for me to zoom, but I hope that helps. And if that should probably get you through the lab just fine. And then we'll get together on Tuesday if you are still struggling. All right, see you then.